Hi guys. So sorry for the interruption of live session which was conducted on cycloalkanes in 60 minutes. That is just due to network error. Please hope you understand. Now this is the continuity of that live session. Here you are going to get most important and typical examples which will be very important for your competitive examinations. So watch this video completely. Okay, right. So in the previous live session we are interrupted at this example, so we are going to continue from that. Okay, here we have two bromines at 1, 2 position in cis relation on planar cyclohexane. So already we have seen that the substrates at 1, 2 position in cis relation on planar cyclohexane converts into axial axial or equatorial equatorial in relationship in its or in respective chair conformations. Okay, now just draw them. Here the two groups or two bromines must be axial axial on one conformation, and in another conformation they must be equatorial in relation. So which one is the most stable? This is the question. Okay, here to give answer for this problem, so simply you can choose the second one as the most stable because you cannot see diaxial interactions as we seen for this bromines which are axial on the structure or conformation A. So simply we can go with B as the most stable conformation for 1, 2 cis dibromocyclohexane. Okay, but here the solvent will play a major role in deciding which conformation will be exist in that particular solvent as a major conformation of the given compound. Okay, for example, if the solvent is non-polar, okay, just note this point. If the solvent is non-polar, in this condition which conformation of the given compound exists? This is the question. So simply the first one will exist in that and it will be the stable one, because you can see here the two bromines, that means the vectors of dipoles move opposite to each other on this diaxial chair conformation. So in this case the dipole moment is almost zero. So the dipole moments are not going to play any role in deciding which conformation, deciding for this conformation to exist in that solvent. Okay, so in non-polar solvent, here diaxial dibromo cyclohexane chair conformation exist. Okay, so this is the answer. For example, if we have polar solvent, in polar solvent the second one equatorial conformation, where so they are not going to that means simply the dipole moment is not going to zero. Okay, so here the dipole moment can be absorbed. So whenever the dipole moment is absorbed, the polar solvents are suitable, and here in polar solvent equatorial chair conformation of the given compound exist. Okay, right. And just here the solvent can differentiate the stabilities and existence of the given chair conformations of the compound. Okay, right. Now here you can see the next case, cyclohexanone, which is also very important for your competitive purpose. That is the substituted cyclohexanone. Okay, so here we can see by just substituting alkyl group at second position or alpha position to this cyclohexanone chair conformation. Okay, so which one is the most stable? So simply we can go with A, because here the diaxial interactions are nil, and whereas you can see the diaxial interactions are absorbed. Okay, and another possible way where the cyclohexanone with equatorial alkyl groups minimizes, okay, minimizes the here we can say A1, 3 or diaxial interactions. Okay, here we have keto group, that's why there are no hydrogens. So here further minimization of 1 comma 3 diaxial interactions, that's why always or in most of the cases, okay, alkyl group prefer to exist in equatorial relation with this keto functional group of that cyclohexanone chair conformation. Okay, right, just remember that point. And in the next case we can see alpha haloketo effect. So just take it, alpha haloketone effect. So here we need to consider the dipole moments. Okay, now just take the example here, the cyclohexanone. Here we have chlorine and another conformation of it where the chlorine is equatorial. Okay, in the first case axial, in second case equatorial. Okay, right, which one is the most stable? So simply we can go with solvents. Okay, solvent effect, right? And here in apolar solvent, okay, in apolar solvent the axial chlorine, that means the axially substituted, halo substituted cyclohexanone chair conformation is more stable than equatorially substituted cyclohexanone. Okay, right. And here why? Because in apolar the dipoles almost they're minimizing. Okay, so due to the opposite vector, so simply in apolar solvents, the axial halo cyclohexanone chair conformations are more stable than equatorial halo cyclohexanone chair conformations. So this is simply alpha halo ketone effect. And in polar solvents, already we have discussed in the previous example, so equatorial chlorine will give dipole moment, that is dipole moment is not going to minimize, it increases. So whenever dipole moment increases, the polarity of that cyclohexanone chair conformation increases and it will be more stable in polar solvent. Okay, right. And next example I'm going to give here, so just try to find which one is the most stable. So here we have two chair conformations but heteroatoms oxygens are there. Okay, and in another one, another chain conformation, here we have axial. So in both the cases methyl groups are axials. Which one is the most stable? This is the question. Okay, right, to give the answer we need to look at the heteroatom here in the chain conformation. So just remember that in chain conformation where the oxygens are there, the carbon oxygen bond length, okay, the carbon oxygen bond lengths are shorter when we compared with carbon carbon bond length. So due to the shorter bond lengths, here you can see that a strong diaxial interactions are observed. So whenever strong diaxial interactions are observed, high strain is observed in this conformation. Okay, and whereas when we compared with the second one, so second one is the most stable chair conformation when we compared both of this. Okay, the reason is the carbon oxygen bond length are very short when we compare with carbon carbon bond lengths. Due to that, high steric 1 comma 3 diaxial interactions are observed in heteroatom oxygen substituted chair conformations when we compared with normal cyclohexanes. Okay, so that's why the second one is the most stable when we compared with the first one. Okay, so just remember the concept on it, and you may give you may come across with different examples on it. Okay, right, now try to look at all these examples. Okay, so first I'm going to give the pyranone. Okay, so these rings are very very important in carbohydrates. Okay, right, and here we have methoxy group. So here, Okay, here it is equatorial, here it is axial. Which one is the most stable? This is the question. And next case, just draw the another one. Here we have acetate. Okay, that is in axial position, and here we have equatorial position. And the next case, here we have chlorine here axial in position, and here we have equatorial in position. If you observe all of this, okay, so the first one is 67% existent. For the second one, 86% existent when we compare with the second one. Okay, that is equatorial one. Here it is almost 94%. So the major confirmations are axial confirmations of it. Okay, so that means simply these are the most stable cases when we compare with these. But in general, the equatorial substituted cyclohex, that means chair conformations are stable. What is the reason here why axially substituted chair conformations are stable? So simply we need to look at anomeric effect. Okay, anomeric effect, that is C1. In anomeric effect, just remember the simple word C1 substituent axial in position, always axial in position. Here you can see this is the C1 case, 1 2 3 4 5 6, like that. Okay, right, at C1 carbon, in anomeric effect, the group with more electronegative atom in that group should exist in axial position. What is the reason here? The lone pair of electrons on ring axis and move here, and the bond cleaves here. Once again, the methoxy group attack here in axial position, and this double bond moves on to oxygen to compensate the positive charge. Okay, so due to this possibility, the axially substituted pyranone rings or most chair conformations are more stable than equatorial conformations, and we can simply call it as anomeric effect. Okay, right, and just remember that polar solvent, just as we seen in the previous cases, polar solvents favor equatorial chair conformations, and apolar solvents favor axial chair conformations. Okay, so just remember these examples, and now we will look at another typical one. Right, and just try to take this example. So which one is the most stable one? Okay, right, here once again we need to look at the carbon and heteroatom bond lengths. We know that sulfur is somewhat bigger than oxygen, so that's why the bond length is high in this sulfur substitute, that means sulfur heteroatom containing chair conformation. So whenever the bond length is high, okay, whenever the bond length is high, then we can see the distance between diaxial interactions when we compare with this. So whenever the distance increases for 1,3 diaxial interactions, then the steric repulsions decreases and energy decreases. When we compare with this, the bond length of carbon and sulfur is higher. That's why the first one is having highest energy when we compare with the second one. So based on this, we can conclude that the second chair conformation, which is having oxygen as a heteroatom in that chair conformation, is more stable when we compare with sulfur containing chair conformation. Okay, right, and I have given the example, that means the question, so you can see on our CHEMMaster community tab on that particular question, so which one is the most stable. Okay, here I'm just giving the structures directly. Okay, try to look at the question. So no one answered that question. Okay, so here I'm going to reveal the answer with the concept. So just try to look at which one is the stablest one. Okay, this is the question is given, right? And if you're interested, you can visit chemmasters.online website where you can practice very high standard online test series to boost your success rate along with the best concept oriented courses. Okay, so these are the different structures are given in that question. Which one is the most stable one? Okay, the answer is so simply A. Okay, so how A is the most stable, and some of the aspirants chosen second as the most stable. So based on that, it is just looking like axial in position. Okay, that is absolutely wrong. Here we need to look at anomeric effect. Okay, and here we can see two types of anomeric effects. Okay, so here one is axial anomeric effect, or simply we can say endo anomeric effect. Okay, and another one is in equatorial position also the lone pair of electrons moves here. Okay, so here if we have oxygen, just move here, axial equatorial methaxy group cleaves from it. Once again methaxy group from equatorial position attack here, and double bond moves onto oxygen to compensate the positive charge on it. Okay, so this kind of effect is called as exo anomeric effect, and this is endo anomeric effect. So here in the first example, you can see they are 90 degrees apart from each other. That's why if you look at this ring, this oxygen is equatorial. And if you consider this ring, this oxygen is equatorial for it. Okay, so that means they are almost so 90 degrees angles. Okay, right. And in this case, so sorry, what you say, they are axials. Okay, they are axial and axial. Here you can see two anomeric effects are observed in this structure. Okay, so here is the possibility one. Whenever this lone pair electrons moves here, this bond cleaves, and whenever these electrons moves here, this bond cleaves. Okay, so two anomeric effects are observed. That's why this structure is more stable. And here in this case, only one anomeric effect is observed. Okay, so here and here, only one anomeric effect. And if you see this one, there is no possibility for anomeric effect. So that's why here the first structure is the most stable one when we compare with the second one and third one. What is the order? So this is the correct order of stability of the given structures based on the anomeric effect. Okay, right. And we can also see a reverse anomeric effect, and we can discuss in the next lecture. And thank you very much. And I hope you can understand. So a live session was just disturbed due to network error. And if you're interested, you can visit chemmasters.online website, and you can join on the best concept oriented courses, and where you can get live lessons also, and you can practice high standard online test series. Okay, so thank you very much, and just subscribe the channel and like the video, and you will get more update on it. Okay, thank you very much.